created by Mindsticks Foundation Trust.
Hello, students. Welcome. Today, we're going to methodically build our mastery of circle geometry by exploring 5 key areas: intercepted arcs explained, the inscribed angle theorem, understanding cyclic quadrilaterals, corollaries and key theorems, and finally, solving geometry examples. Let's get right into it.
Section 1. Intercepted arcs explained.
All right, let's unpack this. What exactly is an intercepted arc? Well, it's essentially the portion of the circle that gets caught right inside the arms of an angle. It's our very first building block for today. Think of the angle as a pair of straight lines cutting directly through the circle. That curved path trapped between those lines, that is exactly what we call the intercepted arc.
Now, I want you to pay close attention to figure 343 on your screen. Notice how an angle can intercept just a single arc, as you can see in the first 3 diagrams. Or it can actually intercept 2 distinct arcs if the vertex is positioned outside the circle, like in figures 4 and 6. And look at this. It brilliantly illustrates that an arm of the angle can even touch the circle purely as a tangent. There are quite a few variations, but the fundamental definition, it remains exactly the same.
Section 2. The inscribed angle theorem.
This brings us to a truly crucial point, a core mathematical truth. The inscribed angle theorem states that the measure of an inscribed angle is exactly half the measure of the arc intercepted by it. Think about that for a second. The angle sitting directly on the circle's edge is half of the arc it creates. So if you know the arc, you know the angle, and vice versa. It really is a beautiful piece of geometric logic. Take a look at figure 3.45. Here, we need to prove that angle BAC is exactly half of arc BDC. Just notice how the vertex A rests perfectly right there on the circumference. Let's walk through the logical deduction step by step together, exactly as we would on a chalkboard. We start by drawing a construction line straight through the center. We'll call it ray AO. Now, because all radii of the exact same circle are equal, we've just formed isosceles triangles. We apply the theorem of isosceles triangles for triangle AOC, and then use the exterior angle theorem. By adding these beautifully derived parts together, we mathematically prove that the inscribed angle is absolutely half the intercepted arc. Fascinating, isn't it?
Section 3. Understanding cyclic quadrilaterals.
By definition, a cyclic quadrilateral is a quadrilateral where all 4 vertices lie on the exact same circle. That means if you can draw a single circle that completely touches all 4 corners or vertices of a 4-sided shape, congratulations, you have a cyclic quadrilateral. Now, what is really interesting here is figure 3.49. Observe this carefully. Our theorem states that the opposite angles of this specific shape add up to exactly 180 degrees. In geometry, we call this being supplementary.
Following the proof logically, let's look at the opposing inscribed angles. Arc ABC is intercepted by angle ADC, making the angle half the arc. In return, angle ABC intercepts arc ADC. So when we add those 2 inscribed angles together, their combined intercepted arcs cover the entire 360-degree circle. Therefore, half of 360 gives us exactly 180 degrees. It's a very elegant, foolproof conclusion.
Section 4. Corollaries and key theorems.
Comparing these 2 figures simultaneously, we see on the left that angles inscribed in the exact same arc are absolutely congruent. They are identical in measure. And on the right, we see a fascinating special case. An angle inscribed in a perfect semicircle is always, without exception, a 90-degree right angle. No way around it. Before we proceed further, I want you to pause and think about this reverse scenario. If you are given a quadrilateral and you happen to discover that the opposite angles add up to exactly 180 degrees, what must be true about that shape? Using deductive logic, the converse of the cyclic quadrilateral theorem tells us that a circumcircle must exist for these 4 points. The quadrilateral must be cyclic. This means if the angles meet that 180-degree condition, the circle is mathematically guaranteed to fit around them perfectly.
Section 5. Solving geometry examples. All right, time to lock in our knowledge by summarizing the key theorems. Keep these firmly in mind as your essential toolkit. The inscribed angle is half the intercepted arc. Angles inscribed in the same arc are congruent. An angle in a semicircle is a right angle. Opposite angles of a cyclic quadrilateral are supplementary. And finally, the exterior angle of a cyclic quadrilateral is congruent to the opposite interior angle.
These 5 principles are literally going to guide you through almost any circle geometry problem you encounter.
Let's analyze solved example 1 together. Looking closely at figure 3.51, we are given an inscribed angle at L measuring exactly 35 degrees. We also know that chord LM is congruent to chord LN.
Methodically breaking down the calculation, we use the inscribed angle theorem first. If angle L is 35 degrees, then its intercepted arc, MN, must be double that, so 70 degrees. Next, we subtract that 70 from the total 360 degrees of the circle to find our remaining arc, MLN. That gives us 290 degrees. Finally, because the chords are congruent, we simply divide 290 equally by 2. Therefore, arc LM measures exactly 145 degrees. See how seamlessly it all comes together? I want to leave you with this final thought to really test your grasp of the material. How would you apply these exact same tools if the chords intersect inside or outside the circle, as seen in the remaining examples? The logic remains precisely the same. Keep practicing methodically, students, and you will soon see that these geometric truths are truly the secret to unlocking the shapes of the world around us. Happy solving!